Welcome you in the lecture series of random processes, detection and estimation. It is sixth lecture of this series. In the previous lecture we have discussed about some special distribution functions, moment generating function, characteristic function, bivariate random variables, joint distribution function, one function of one random variable, two function of two random variables. In this lecture we will discuss about joint functions and the concept of random process. And the outline of this lecture are: we will discuss about joint moment, correlation and covariance, joint moment generating function, joint characteristic function, conditional distribution, conditional expected values, conditional variance, and the concept of central limit theorem, and the concept of random process. Also, we will discuss about the mean of random process and autocorrelation and the autocorrelation function. And with this lecture, you will able to explain how to find the joint moment of bivariate random variable, the significance of correlation and covariance, and the importance of the central limit theorem. You will also able to explain the concept of random process and its properties, and the mean of the random process, and also you will able to explain the significance of the autocorrelation function. Now we will start with the joint moment. Consider a pair of random variable x and y, then k and nth moment of a bivariate random variable xy is mkn is equal to expected value of e to the power k and y to the power n. And for the discrete case, it will be the summation with x and y, x to the power k, y to the power n, and the joint PMF of x and y. And for the continuous case, the double integration minus infinity to infinity is x to the power k, y to the power n, and the joint CDF and the joint PDF of bivariate random variable x and y for the continuous case. And this expected value of x is to the power k, y to the power n is known as the joint moment. And if n is equal to 0, we will get the kth moment of the random variable x. And if k is equal to 0, we will get the nth moment of random variable y. Now let's consider a case when n is equal to 0 and k is equal to 1. So in this case m10, it will be the expected value of x. It will be the double integration minus infinity to infinity random variable x and the joint PDF of random variable, and we have taken the integration with respect to x and y. So I can separate these integration with respect to x and y. I have put x here, so minus infinity to infinity x and integration minus infinity to infinity the joint PDF of random variable xy. And you know, this is the marginal PDF of random variable x, so I can write ex will be minus infinity to infinity x fx dx. And so you can see here that when k is equal to 1 and n is equal to 0, it gives the first moment of the random variable x. And similarly, when k is equal to 0 and n is equal to 1, the m01 will be the expected value of y, and it will be minus infinity to infinity y fy y dy. And this is, you can see, when k is equal to 0 and is equal to 1, you get the first moment of random variable y. Now we consider the correlation. You know that expected value of x is to the power k, y is to the power n will be minus infinity to infinity x is to the power k, y is to the power n, and the joint PDF of random variable x and y. And if here n and k are 1, then the joint moment is known as the correlation of the random variable x and y, which is the expectation of exy. So the correlation is the expected value of exy, and it will be denoted by minus infinity to infinity xy and the joint PDF of random variable x and y. And the covariance. If x, ex and ey are the mean values of random variable x and y, then the two central random variable will be x minus ex and y minus ey, and the correlation of these two central random variable is the covariance of random variable x and y. So mathematically it can be written as covariance xy means the expected value of central random variable x and y. So it is expected value x minus ex and y minus ey. So you can write here expected value of exy minus ex ey, and this is the correlation. This is the correlation between x and y. So if sigma x square and sigma y square are the variance of x and y, and when covariance xy is normalized with this value sigma x sigma y, we get the correlation coefficient of xy, means the correlation coefficient will be covariance xy upon sigma x sigma y, and this correlation coefficient is the measure of linear dependency between x and y, and if the covariance is equal to 0, then we say that x and y are uncorrelated. So covariance is 0 means exy ex ey will be 0. This means exy correlation, it will be equal to the mean of x and mean of y. So the correlation will be the product of the mean value of random variable x and y, or you can say the correlation coefficient will be 0. So these are the conditions when we say that x and y are uncorrelated. So here if the correlation exy means expected value of xy is 0, then we can say that the two random variable xy are orthogonal. And if random variable xy are independent, then the expected value of exy, or you can say the correlation between xy, it will be the expected value of x into expected value of y, or you can say that the covariance will be 0 here if x and y are independent. Now consider an example. The joint PDF of bivariate random variable xy is k x plus y when x and y are between 0 to 2, else it is 0, where k is constant. So the first part is find the value of k, and you know the double integration of the joint PDF with respect to x and y will be 1. So from here you can find the value of x between 0 to 2 and value of y between 0 to 2, and we can integrate the joint PDF k x plus y dx dy is equal to 1. So from this integration, after solving this integration, you will get the value of constant k is 1 by 8. And the second part is find the marginal PDF of x and y. You know if you want to find out the marginal PDF of x, so you have to integrate the joint PDF with respect to y. So after integrating, you will get fxx is equal to 1 by 4 x plus 1, and fxx will be equal to 1 by 4 x plus 1 when x between 0 to 2, else it is 0. And similarly the marginal PDF of y fyy, you can get this by integrating the joint PDF with respect to x, and you will get 1 by 4 y plus 1. And so fyy means marginal PDF can be defined by 1 by 4 y plus 1 when y is between 0 to 2, else it is 0. And in the third part, you have to find are x and y independent. So here you can see fxx and fyy means marginal PDFs. It will be 1 by 4 x plus 1 and 1 by 4 x plus 1 by 4 y plus 1. So here you can see 1 by 16 x plus 1 y plus 1, but it is not equal to the joint PDF, and you know when not independent random variables. Now we'll come to another concept, joint moment generating function. The joint moment generating function mxy t1 t2 of two random variable xy is the expected value of e to the power t1x plus t2x, or in the discrete form you can say the summation k0 to infinity and n0 to infinity, t1 is to the power k and t2 is to the power n factorial and factorial k, and expected value of x to the power k, y is to the power n. And there is important lemma related to the moment generating function. If two random variables have the same moment generating functions, then they must have the same distribution. Now another is the joint characteristic function. The joint characteristic function phi xy omega 1 omega 2 of two random variables x and y is phi is expected value of e to the power omega 1 x plus omega 2 x, or in discrete form it is the summation with x and with I and k e to the power I e to the power j omega 1 x I plus omega 2 y k, and the joint PMF. And in the continuous case it is the double integration of e to the power omega 1 x plus omega 2 x, and joint PDF of random variable x and y. Here omega 1 and omega 2 are the real variables, and expression of this equation is recognized as the two-dimensional Fourier transform of the joint PDF x and y. So from the inverse Fourier transform we can find out the joint PDF is equal to 1 by 2 pi square double integration of phi x y omega 1 omega 2 e to the power j omega 1 x plus omega 2 y d omega 1 d omega 2. So this is the inverse Fourier transform. And now we are coming to the conditional PMF. That if x and y is a discrete bivariate random variable with joint PMF pxy xi yj, then the conditional PMF of y given x is equal to xi. So with the given value of x is equal to xi, the conditional PMF py by x, it will be the joint PMF of xy divided by the probability of x at x is equal to xi, where xi greater than 0. And similarly the probability y by x, or conditional PMF x by y, so it will be the joint PMF of xy divided by the probability of y with y is equal to yj, and where the probability of yj greater than 0. And the properties of the PMF, because this is the probability, so it will lie between 0 and 1, and the summation of all probability will be 1. And here if x and y are independent, then the conditional PMF y by x, it will be the py, and px by y, it will be the px, because the occurrence of x will not affect the occurrence of y. So this is the property of the PMF. Now the conditional PDF, if x and y is a continuous bivariate random variable with joint PDF fxy, and the conditional PDF y by x given x is equal to x, so it will be equal to the joint PDF of xy divided by the PDF of x, where the PDF of x greater than 0. And similarly the conditional PDF x by y, it will be the joint PDF of xy divided by the PDF of y, where the PDF of y greater than 0. And the properties, the conditional PDF will always be greater than 0, means it is positive, and the integration means the summation of all PDFs or the area under the PDF will be equal to 1. And if x and y are independent, then the conditional PDF y by x is equal to the PDF of y, and the conditional PDF y x by y will be equal to the PDF of x. Now we'll come to the conditional expectation of random variable. The conditional expectation of y given x is equal to x. So it will be the expected value of y when x is equal to x given. So it will be integration y minus infinity to infinity y, and the conditional PDF y by x, and you can denote it is mu y by x. And similarly, the conditional expectation of x given y is equal to y, it will be the integration x minus infinity to infinity x, the conditional PDF x by y, and it is denoted by mu x by y. And the conditional variance of y when x is equal to x given, so it will be the expected value of y minus mu y by x, means the random variable y, and the conditional expected value of y by x whole square given x is equal to x, and variance of the conditional variance of x given y is equal to y, it will be the expected value whole square of the random variable x minus the conditional expected value given y is equal to y. Now consider the example. The joint PDF of bivariate random variable x is 2 when y is between 0 to x and x is between y to 1, else it is 0. Find the corresponding PDF of y by x and PDF of x by y. So you know the marginal PDF of x, you can find out the marginal PDF after integrating the joint PDF with respect to y. So you will get the 2x, fxx is 2x, and similarly fyy marginal PDF of y, you have to integrate the joint PDF with respect to x. So you will get 2 1 minus y. Here x is between in fxx x is between 0 to 1, and fyy where the y is between 0 to 1. So similarly you can find out the conditional PDF. It will be the joint PDF divided by the PDF of x, and you have already found out the marginal PDF of x. So it is 2 by 2x or 1 by x. Here x is between 0 to 1, and or you can say x between y to 1. And similarly the conditional PDF of x by y, so it will be the joint PDF of x divided by the PDF of y. So it will be 1 by y, where y is between 0 to x and x is between 0 to 1. And in the other part you have to find out the conditional mean ey by x and ex by y. So the conditional mean means, you know, integration y minus infinity to infinity y, and the conditional PDF y by x, and you have already calculated this. So it is y0 to x, the value the range of y is between 0 to x, and y, and this is the conditional PDF y by x, it is 1 by x. So you have calculated it is x by 2 when x is between 0 to 1. And similarly the conditional mean x by y, it will be the integration x and the conditional PDF x by y. So you have calculated this 1 plus y by 2, where y is between 0 to 1. So you can see here that a conditional expected value y by x is a function of x only, and conditional e x by y is a function of only y. Now, in the another part, compute the conditional variance y by x and variance x by y. You know the variance y by x, it will be the expected value y minus x, conditional mean whole square given x is equal to x. So you can take integration y minus x by 2, this is the conditional mean, the whole square of y minus x by 2, and the conditional PDF y by x. So after solving this, you will get x square by 12, the value of conditional variance y by x. Similarly, the conditional variance x by y, you can calculate 1 minus y whole square by 12. And now we come to the upper bound on the tail probability. In evaluating the performance of a digital communication system, it is necessary to determine the area under the tail of the PDF. We refer this area as the tail probability, as you can see in this figure. Now we present the upper bound on the tail probability from the Chebyshev inequalities. We know that the variance of a random variable measures the width of the PDF, and the Chebyshev rules express this quality of variance in an alternate manner. The PDF fxx of a random variable is symmetrical about mean, and let us consider the mean is 0. The probability of random variable x, if x is such that the mode of x greater than equal to epsilon, that is the area under the shaded region. You can see here under the shaded region. In the PDF curve, the probability of mode x greater than equal to epsilon will decrease as epsilon increases, and the Chebyshev rules provide an upper bound on this tail probability in terms of sigma square epsilon square, and the probability of mode x greater than equal to epsilon will be less than equal to sigma square upon epsilon square, where sigma square is the variance, and this is the upper bound on the tail probability. Now we will consider the law of large numbers. First we will consider the weak law of large numbers. Let x1, x2, xn are the sample sequence of independent identically distributed random variables, each with a finite mean mu, and xn is equal to 1 by n summation I 1 to n xi, means 1 by n x1 plus x2 plus xn. This means xn bar is the sample mean. And for epsilon greater than 0, limit n tends to infinity, the probability of mode x bar minus mu greater than epsilon will be 0. This equation is known as the weak law of large numbers, and this tells how a sequence of probability converges. And another is the strong law of large numbers. Let x1, x2, xn are the sample means, sample sequence of random variable of independent identically distributed random variables, each with mean mu. And for epsilon greater than 0, the probability limit n tends to infinity, mode x bar minus mu greater than epsilon equal to 0. This equation is known as a strong law of large numbers, and this equation tells how the sequence of the random variables behaves in the limit. Now we are able to explain the central limit theorem. The central limit theorem is one of the most remarkable results in the probability theory. This theorem states that the sum of a large number of random variables will have approximately the normal distribution. Let x1, x2, xn are the sequence of independent identically distributed random variables, and here the sample mean xn bar, it is 1 by n x1 plus x2 plus xn, and let us consider another random variable zn. It will be the under root n x bar minus mu. So this Zn, the central limit theorem states that the distribution of this Zn tends to normal as n tends to infinity. This means limit n tends to infinity, Zn will be the normal distribution with mean 0 and variance sigma square. And if we consider Zn as and root n into the sample mean minus mu upon sigma, then when we have n tends to infinity, then this the distribution of this Zn will be the standard normal distribution with mean 0 and variance 1. This is the central limit theorem. So the central limit theorem tells us that for a larger n, then the distribution of the sum of x1 plus x2 xn approximately a normal regardless of the form of the distribution of the individual random variables x1, x2 and xn. So now we are coming to the random process or stochastic process. In the real world of engineering and science, it is necessary that we able to deal with the time waveform. We frequently encounter random time waveform in practical system, like a desired signal is often mixed with a random waveform, that is noise, and this noise limits the performance of the system. And the concept of random process is the logical extension of the random variables. This extension is necessary for statistical analysis of the random signal encountered in the communication systems such as voice signal, video signal, digital data, electronic signals. These signals are not only function of time but random as well. And consider a random experiment involving the measurement of air temperature of a certain place at 10 am daily. The temperature is random variable because it takes different values every day. The air temperature at a particular location is the function of time also. A random variable that is a function of time is known as the random process or stochastic process. Now, to specify the random process xt, we need to record daily temperature for each instant of time of the day. This record gives one waveform xtsi. So here is the one waveform xtsi. Si indicates the day for which the record was taken. So for S1 means for the first day, the sample waveform is xts1, or you can represent it as x1t, and for the second day xts2, and you can represent it as x2t, and for the nth day it is xnt. So these are the ensemble waveforms, and this procedure was taken has to be repeated every day for a large number of days. The collection of all the possible waveforms, known as the ensemble of the random process, is the ensemble of the random process means ensemble of the all waveforms. So S1 belongs to the S1t process, S2 belongs to the X2t process, and Sn belongs to the Xnt process. And in the case of random variable, these are the sample points S1t, S2t, S1, Sn. But in the case of random process, these are the waveforms, and which is correspond to outcome and of the waveforms. And the set of sample function is x1t, x2t, xnt. You can say the S1, S2, Sn. This set is denoted by xit, where I is 1, 2, 3, 4 and so on, and the sample function or the waveform x1t, you can say this is correspond to s1, and x2t is correspond to s1, as I told you. And you can see here for the time instant t1, if this is the time instant t1, I measure in the sample the random process. If I measure and the value of this random process at the time t1, it will be the x1, x2, xn. So these are the random variables at a particular time. So the value at a particular time t1, the random process will be the random variable. So I denote this random process at t is equal to t1, means if I measure the random process at t1, so x t1 will be the random variable x1, which is having the value of x1, x2, xn. And similarly at the time instant t2, if I measure this random process xt, it will give you the random variable x2, and the value of this random variable will be the x1 dash, x2 dash and xn dash. So these are the if I measure the random process at a particular time, it will give you the random variable, and so the set of waveforms at t is equal to ti is a random variable. Here you can see. So with the instant t1, t2, t3, we will have random variable xt1, xt2, xn. So here xt will be the collection of xt1, xt2, xt3, means at the different time you will have the random process, and these are the different random variables. And xt1 means at time t1, the random variable x1 will have the value x1, x2, xn, and xt2, the random variable x2 will have the value x1 dash, x2 dash, xn dash, and so on. Now we'll consider the probabilistic description of random process or stochastic process. Let xt1 is equal to x1 is a random variable which is measured from the random process xt for a fixed time t1. Then its CDF, it will be fx1 t1, means the probability xt1 less than equal to x1. This is the random variable x1. This is the first order distribution of xt, and similarly xt2 is equal to x2 is another random variable which is measured from random process at a fixed time t2, and so there are two random variable x1 and x2 now at time t1, t2. The joint distribution will be fx1, x2, x1, x2 at time t1, t2. It will be the probability of first random variable xt1 less than equal to x1, and the probability of second random variable less than equal to x2. This is the joint probability, or you can say this is the joint distribution, and this is the second order distribution of the random process xt. So similarly the nth order joint CDF of random process, it will be x1, fx1, x2 to xn with time t1, t2, to tn. It will be the probability of first random variable less than equal to x, second random variable less than equal to x2, and nth random variable less than equal to xn. And if xt random process is discrete time process, then the joint PMF will be the PMF x1, x2 at time t1 to tn. It will be the probability with random variable xt1 is equal to x1, and the random variable xtn is equal to xn. And if xt is a continuous time process, then xt is satisfied by the collection of PDFs or joint probability density functions of a random variable, and it will be the derivative of the CDF, and so it is del n upon del x1, del x2, del xn, and the joint CDF, nth moment CDF of random process. The mean of the random process xt. The mean, autocorrelation, covariance, cross correlation of a random process are important statistical parameters. These parameters plays a key role to characterize the statistical process whose probability density cannot be determined directly. So mean of a random process xt, denoted by mu xt, or you can say the expected value of xt, and autocorrelation function. The random process xt measured at time t1 will be the random variable x1, and the expected value of this random variable t1 means the random variable x1 will be the integration minus infinity to infinity x1, and the PDF of x1 at time t1 or t dx1. And similarly, if the expected value of the random variable xt2, it will be the expected value of random variable x2, or applying the e operator you will get the integration x2 fx x2 t dx2. So now the correlation is the expected value of x1 and x2 means the expected value of xt1 or xt2, and it will be denoted by as rxx t1 t2 or rxx t2 minus t1. This is the autocorrelation function of a random process xt, rxx t2 minus t1, and when t2 minus t1 is tau, then autocorrelation function will be the expected value of xt1 and xt1 plus tau, or you can say the expected value of xt1 and xt1 minus tau. And also it can be represented as the autocorrelation function. It will be the expected value of xt and xt plus tau, or expected value of xt minus tau. And the properties of autocorrelation function. This is the first property of autocorrelation function. Mode of autocorrelation function at time lag tau, it will be less than equal to rxx time lag 0. So this means the autocorrelation function of a random process has the maximum magnitude at 0 time lag. So if the random process xt changes with time rapidly, the autocorrelation function will decrease rapidly from its maximum value rxx naught, and as tau increases. And the second property is rxx minus tau, it will be the rxx tau. This means the autocorrelation function of a random process is the even function of the time lag, or you can say that the autocorrelation function has even symmetry. And the third property is rxx 0, it will be the expected value of x square t greater than equal to 0. This means that the square value of the random process is equal to the autocorrelation function of the process for 0 time lag. And another property of the random process is the autocovariance function. Let the random variable xt1 and xt2 are observed by the random process xt at time t1 and t2. Then the autocovariance function of the stochastic process cxx t1 t2, it will be the covariance xt1 xt2, and you know the covariance, it will be the correlation e xt1 xt2 minus the mean of xt1 and mean of xt2. And if t1 minus t2 tau, so cx tau autocovariance, it will be the autocorrelation xt minus tau minus ext whole square of the mean of the random process, because the mean value will unchanged from t1 to t2, so that's why I have written the whole square here. So here you got the autocovariance will be the autocorrelation minus the expected value of xt whole square of the expected value of a random process. And if the random process xt has zero mean, this means ext is 0, then the autocorrelation function and autocovariance functions are equal, are same. And again, you know, if tau is 0, then cxx0, it will be ext minus tau minus whole square of expected value of random process, and it will be the autocorrelation minus the whole square of the mean of the random process. So you will get here, this is the this is sigma x square t. This is the variance of the random process xt, because here rx tau, it will be the expected value of x square t. So expected value of x square t minus whole square of the expected value of xt, it is the variance of random process xt. So for the time being, this was lecture 6 on the lecture series of random processes detection and estimation. In the next lecture, we will discuss about the classification of random process, means stationary random process, non-stationary random process, wide sense stationary random process, Markov process, and cross correlation function, cross covariance function, and power spectral density. Till then, thanks for listening this lecture. Thank you.